moving on from a particle in an infinitely deep box, we're going to explore how particles interact with finite potentials of various widths and types, as you can see in our setup here. So to attempt to solve one of these problems, it's a little bit more complicated than the particle in a infinitely deep box, but we approach it in the exact same way. So the first step is to set up the Schrodinger equation for each different potential region of the box that we have. So here you can see I've split up the potential into four different regions. We have a long potential of V naught that's kind of infinitely long. Then we have a very short potential of V1, and then in between those two we have regions of zero potential. So to start off, again, we just need to solve the Schrodinger equation. And first we need to set it up before we can solve it. So I'll go ahead and copy this down here. I've rearranged the Schrodinger equation in terms of the second derivative of the wave function, which helps to make sense of it. And so to solve the Schrodinger equation, we just need to substitute in our various potentials. So in this first region, our potential is V naught. So we can go ahead and substitute in V naught here. And then what we can recognize, and this will help us when solving the equation, is that our E minus V naught is a negative number because we're particularly interested in particles that are in our finite box. So that means they have less energy than the potential V naught. And so to make sense of this, we're going to change the sign of this. So we're going to switch the order. So V naught minus E, we'll pull out the -1, and then we'll get rid of that negative as well. And this helps us recognize that when our energy is lower than our potential V naught, our number is positive, which has important implications for solving the differential equation. All right, for the second region, we can go ahead and paste in our Schrodinger equation here, and our potential in this case is 0. So we can go ahead and erase our potential and recognize that we have the same differential equation that we did for the particle in a infinitely deep box. And this is also going to be true of our section 4 is going to have the same solution. For section 3, we're going to have the same solution as section 1, except recognizing that we have a new potential here just because of the way I've set up the problem. So here we have V1 minus E rather than V naught minus E. And then for region 4, it's the exact same solution as region 2 because there is no potential. Okay, so now that we have set up the Schrodinger equations, we can attempt to solve the Schrodinger equation. And the solutions to the Schrodinger equation will give us the wave functions. So the question we need to ask is what kind of functions are solutions to these differential equations for the various regions? So let's start with section 2. Section 2 is going to be a particle in a box similar to our particle in our infinitely deep box from the last video. And for this particle, it's going to have a very similar solution. So we need to take two derivatives of our wave function and end up with our wave function again multiplied by a negative constant. One way to do that is the way we saw before with sine and cosine functions. So it's going to be equal to these sine functions. So see sine kx plus d cosine kx. And I'm going to have different k's here in different parts of the problem. The k's are essentially representing the square root of these terms that are multiplied by my wave function. And so you can see there's 3 different ones, so there'll be 3 different k's. All right, so it has the same solution as before, and these capital letters, these C's and these D's here, are just representing that we don't exactly know how much the wave function looks like each of these different possible solutions. We can also do region 4. So region 4 is going to be the same, so the exact same problem, and it could have the exact same solution. However, when we're in region 4, we're recognizing that our particle is no longer in a box. It's in this infinite going from B to infinity, and there's no box there. So it's going to act more like a traveling wave. So it's going to make more sense for us to represent our wave as a traveling wave. So rather than sine of kx, we can represent it as e to the I kx. And we can also have a component going in the reverse direction, e to the minus I k1x. So these are the 2 possible solutions to the same differential equation in region 2 and 4, and we use them in the forms that we do because it makes the most sense for the kinds of questions we're asking. So region 1 and 3 are, as you can see, they're a fundamentally different problem. So rather than taking two derivatives of our function and multiplying that by a negative constant, we're rather multiplying it by a positive constant. So you can see if you take two derivatives of our sine and cosine function here, that when you do that, you do not get a positive number. You always get a negative number. So that means sines and cosines are not good solutions for either of these equations. And the solutions that we're going to need to use are exponentials. So if we have an exponential function, we can take a e to the k0x and then b e to the minus k0x. And these are going to be valid solutions here. If we take two derivatives of this, we'll end up with a positive number multiplied by our wave function. And we can do the same thing here for part 3, and we can have f e to the k2x plus g e to the minus k2x. Again, remembering that all of the k's are just the various different constants that are multiplied by our wave function. From here, we can make some assumptions and cross out some of these terms based on what we need to do with the wave function. So, for example, in section 1, we have these two terms, one that's exponential decay and one that's exponential growth. And remember, one of our properties of our wave function is that our wave function needs to be normalizable. It needs to be normalizable because we want to make probability claims about the wave function. So we need to take the area under the curve of our wave function, and that's going to indicate the probability of finding the particle within that region. So if our wave function goes to infinity, it's not normalizable. We can't set that equal to 1, and we can't have a meaningful probability there. So that means that our wave function in this region 1 can't be exponential growth because that wouldn't be normalizable from 0 to minus infinity. And so that means that we can't actually have this second term here. So this second term has to equal 0, so the b has to equal 0 to prevent the exponential growth. The exponential decay is okay because that's normalizable. In region 2, you'll remember from the particle in an infinitely deep box that we were able to eliminate the cosine term. However, we were able to eliminate the cosine term because of the boundary conditions. And we'll see here as we explore the boundary conditions that they're not the same. So we actually can't eliminate the cosine term here in region 2. In region 3, you might think we should eliminate the exponential growth part of this. However, we can't do that either, and that's because our region 3 is a small finite region. So no matter what the exponential growth is, it will be normalizable over this finite interval. So we can't eliminate that component. However, we can eliminate this component here. We can eliminate I and set that equal to 0. And that's because that e to the minus ikx represents a wave traveling in the reverse x direction. And there's no reason our wave should reverse course once it passes through the barrier. So it would just go in the forward direction and only be explained by that h e to the ik1x term. So this is how you can go and set up the functional forms of the wave equation here and our wave function. But what we might want to do is we might actually want to explicitly solve for this. And this is something that we've done in the homework a couple times, and we won't do this again in class. But if some people may be interested in this for certain applications, and to do that, you have to apply boundary conditions. So our boundary conditions are going to be that our wave functions at the boundaries are equal to each other, and that will give us continuous wave functions. And that's important because our wave function, again, is supposed to represent probability. So if we had two different values for probability, that wouldn't make any sense. We have to have one value of probability, so our wave function has to be continuous. Our second condition for boundary conditions is that our wave function's first derivatives also have to be continuous. And that's because we need to be able to take the second derivative of them because we're plugging them into the Schrodinger equation. So the boundary conditions here are that the wave function at the boundaries have to be equal. So our first part of our wave function at 0 has to equal the second part of the wave function at 0. And we can make the same thing. So the second part at A has to equal the third part at A, and then the third part at B has to equal the fourth part at b. So this is all our boundary conditions, ensuring our wave function is continuous. And then the last condition is that the first derivatives of all of these are also equal to each other, which makes sure our second derivative is also continuous. So we could apply these boundary conditions and then attempt to eliminate the various constants and figure out some stuff about our system. But typically we won't want to do that in this class. I've already tortured you enough making you do that on some homework problems. So the last thing that we could want to do is use our knowledge of the forms of the wave function, so this information here, to sketch the wave function onto our potential curve. And we can do that without explicitly knowing any of these constants. So for example, in region 1, we have to have exponential decay. So we can draw an exponential decay curve here in region 1. And then we know in region 2, our function has to equal this at 0. And so you can see here the fact that this isn't 0 means there is some cosine contribution. So we couldn't have eliminated the cosine term. If this is the lowest energy state, it's going to kind of sort of look like the lowest energy state for a particle in the box. So it's going to go up and then come back down in 1/2 wave, and then again intersect at not quite 0 here. It's going to undergo some form of exponential decay, and then it's going to come out and maybe be a traveling wave here if it has enough energy to come out. We can also do it for a higher energy state. So for a higher energy state, again, we're going to have exponential decay. And then we're going to have something that kind of looks like the second form of the wave function. The second, the one full oscillation, another exponential decay, and then another traveling wave coming out. So we can use our knowledge here of what our functional forms look like to get a pretty good estimation for the wave function at whatever location we care about.